Okay. So last lecture, if you recall, we proved the minimax theorem for zero-sum games. So just to briefly recap, a zero-sum game is just some game in which the two players in the game have strictly opposed incentives. The way we model that is that there's a single function that one player, max, would like to maximize, and the other player, min, has exactly the opposite goal. She would like to minimize this objective. The players have, in general, sort of arbitrary strategy spaces. We just assumed that they were compact and closed so that best responses made sense. So you can take maxes and mins over this set. And in general, in fact, we saw examples of games in which, in general, order of play matters. It can, actually be a real disadvantage to go first and reveal your strategy to your opponent. An example of this is just rock, paper, scissors, in which you're not allowed to randomize. Okay, if I tell you that I'm playing rock, you're going to play paper. So if I go first, I lose. And if I go second, I win. So in rock, paper, scissors, if I'm not allowed to randomize, going first actually is a disadvantage. But the minimax theorem, which we proved, says that if we assume relatively mild regularity conditions, things that are satisfied just by letting me randomize in rock, paper, scissors. So for example, we required that the strategy space be convex. I can take convex combinations of actions. So that means I'm allowed to randomize. We required that the objective function be convex in the minimization player's strategy space and concave in the maximization player's strategy space. That's satisfied by taking expectations over discrete actions, since expectations are linear. Under those assumptions, essentially the assumptions we had needed to make online convex optimization work, in fact, it was, if we were sort of thinking about how well you could do in a zero-sum game, either by going first, by going second, or in fact by playing simultaneously and playing a Nash equilibrium, what the minimax theorem said is that in all three of these scenarios, max goes first, min goes first, or both people simultaneously play a Nash equilibrium of the game, the outcome is payoff equivalent. If everyone plays optimally, there's some value of the game, v, which is the same as the minimax value and the maximin value that everyone will obtain. Okay, so what the minimax theorem says is that under sort of reasonably mild regularity conditions that are nevertheless important, because we know of examples in which the minimax theorem doesn't hold when the conditions are violated, order of play does not matter. Okay. Okay, so let's sort of, why is that interesting? It's interesting for at least two reasons. One is just as an interesting structural statement about zero-sum games. Like sometimes when you are modeling something in the real world, you'll find that some interaction really is reasonably modeled as a zero-sum game. The minimax theorem has a bunch of implications, not least of which is sort of a prescription for optimal play. Right? In general, it's not necessarily optimal to play a minimax strategy in a game because those don't necessarily correspond to Nash equilibria, but in a zero-sum game it does. But another reason why this is useful, and it's sort of something that we're going to start leaning on in the coming lectures, is that it is useful as an algorithm design paradigm. Okay, so like the kinds of algorithms we've been studying so far in this class and that we're going to continue to study are algorithms that have guarantees in adversarial settings, and algorithms that have guarantees in the worst case, no matter what sequence of costs or actions or observations you make. Okay, so like what we're doing in these settings when we give an algorithm, when I write it on the board and then say that no matter what no matter what sequence arises, the algorithm has some nice set of guarantees. What we're doing in these settings is we are committing to a strategy in a big zero-sum game, right? Like you can think about sort of adversarial guarantees as being statements about zero-sum games. there's two players. There's the algorithm player who's deciding on what algorithm to use, for example, to map costs in the past to predictions in the future. And there's the adversary who's trying to come up with a sequence of costs to feed the algorithm. And then there's some objective, the thing we prove a theorem about, for example, regret, that we can think of as the algorithm player trying to minimize and the adversary trying to maximize. And when we prove a regret bound, what we're saying is, even when we go first and commit to an algorithm, like the algorithm that is typically written on the board when we're proving something about it, even when we go first and commit to an algorithm and then allow the adversary to best respond and choose the sequence of losses that would maximize our regret, we can do well. Okay, so the thing that we're sort of trying to prove when we prove a regret bound, you can think of as a statement about, a constructive statement, because we give the algorithm, but a statement about the minimax value of some enormous zero-sum game in which we play the role of selecting the algorithm and our opponents play the role of selecting the cost, and we go first. That's why we need a minimax optimal algorithm. Now, what we know from the minimax theorem, and of course we need to verify that these conditions hold, is that how well you can do in a zero-sum game is invariant to whether you go first or whether the adversary goes first. Now, so far, we've just been sort of proving these regret kinds of guarantees from scratch. We have to come up with clever arguments. There's some, like potential function, the sum of the weights when we're analyzing multiplicative weights. Where does that come from? Who knows? It's just, like pulled out of thin air. But sort of something that we're going to start exploring next class is, well, since it doesn't matter who goes first, if you just want to non-constructively think about the kinds of regret bounds that are possible to obtain in some experts learning setting, for example, it's okay to imagine that the adversary goes first, because the minimax theorem says it doesn't matter who goes first. Well, these learning problems, these online learning problems, they're very much about, trying to predict the future in various ways, right? Like you're trying to select actions that are competitive with the best action in hindsight. Wouldn't that be easy to do if you knew what the best action in hindsight was before you had to select your action? And it turns out, maybe like unsurprisingly, that if the adversary goes first and tells you ahead of time what the distribution of costs is going to be, that it is transparently easy to have no regret. Every day, pick the action that corresponds to the lowest expected loss. Of course, like if you had the luxury to know what the costs were going to be ahead of time before you had to choose your action, these problems would be trivial. But, and maybe this is sort of hinting at the power of the minimax theorem, like non-constructively at least, it's sort of saying, okay, assuming you've checked made sure the conditions of the minimax theorem are satisfied. That's why we're going to need to allow these algorithms to randomize, for example. Assuming the conditions of the minimax theorem are satisfied, when we're trying to think about what is possible in a no-regret setting, we might as well imagine that the adversary goes first and tells us every day the distribution on costs they're going to predict. If it is trivial to get no regret in that case by simply predicting the action that has the lowest expected cost, then that tells us that it's perhaps not trivial, but possible to commit to an algorithm that has the same guarantees. Because the only difference in sort of best responding to the distribution on costs fixed by the adversary and getting no regret, and committing to an algorithm that promises no regret against adversarial sequences, the only difference there is the order of play. Does the algorithm player go first, or does the adversary go first? And the minimax theorem says the order of play doesn't matter. Okay? Now, the minimax theorem, as we've stated it so far, it's not algorithmic. The proof of the minimax theorem was algorithmic, but the minimax theorem was sort of an existential statement. It was a structural statement about zero-sum games. It said that the min-max value of the game is equal to the max-min value of the game, but it didn't say how to compute an equilibrium strategy. Okay. As we start analyzing algorithms, as we start analyzing the power of online algorithms using minimax statements, right, which is going to be, like, it's going to feel like cheating, right? Like a lot of these problems are like really easy if the adversary has to tell you the costs first. As we start doing that, right, the minimax theorem on its own is just going to give us sort of existential statements. There exists an algorithm with these properties, right? Because we know that, the min-max value will be good, and there is some min-max strategy that instantiates the min-max value. The algorithm that will correspond to these kinds of existential arguments that we're going to be developing will be the algorithm that says, okay, every day play a min-max equilibrium of some appropriately defined game. And so in order to make this constructive, in order to make sure that we can actually do this, it's going to be important that we be able to actually compute the min-max equilibria of zero-sum games, not just say something about their value, but have a way of producing an actual object that we can hold in our hands that achieves the min-max value of a game, or at least something close to it. Okay? And so that's what I want to talk about today. I want to think about the actual computational problem, given a zero-sum game, of computing an approximate min-max or max-min equilibrium. Okay, and we're going to have a couple of different ways of doing that. We'll give sort of two qualitatively different ways of doing this computation that sort of require the ability to implement different kinds of primitives. And so both of these ways are going to be useful for us in the various applications we encounter. Okay, so before we, that was sort of like the high level map. Before we go on and actually like write some stuff on the board, are there questions about the sort of general premise? The intention is that as we, maybe not this lecture, we're sort of doing, sort of standard computational stuff, but the intention is that as we start deriving algorithms using these minimax arguments, that all of your minds should be blown. Like this should be like, amazing that we can, analyze a scenario that is like clearly trivial, where the adversary tells us what he's going to do before we need to act, and yet conclude the existence of an algorithm. So, in preparation for your minds being blown, like any like clarification kinds of questions about what I really mean. Yeah. We'll give you. Yes, so like, for example, the first thing we're going to do with the minimax theorem, next lecture is we'll go back and we'll like rederive the multiplicative weights algorithm. Like the multiplicative weights algorithm sort of came out of thin air the first time we derived it. We like gave some algorithm, we came up with some clever analysis, we were like keeping track of these weights. Where did that come from? How would you go about finding that algorithm if you didn't read about it? The first thing we're going to do is derive that algorithm from first principles, just starting from the minimax theorem. Turns out once you know the minimax theorem, it's like obvious that you can get no regret in a sequential prediction problem. That's what the existential statement will say. And you can even compute like a sort of a closed form solution for what the equilibrium strategy that you need to play every day is, and that'll turn out to be basically the multiplicative weights mechanism. And then we're going to start using it in the coming lectures to derive algorithms for things that we haven't seen before. Any other questions? Okay. So like, what are the things we're going to try to compute? So we're going to try to compute not necessarily exact minimax strategies in zero-sum games, but approximate minimax strategies. Sometimes we'll be able to compute exact ones, but for most of the applications we're going to see, approximate ones are going to be good enough. And the nice thing about approximate solutions is we're going to have a lot of flexibility in how to compute them, which is going to come in handy. So let's start by just figuring out what those things are. So, fix any zero-sum game, which, remember, is just defined by strategy space for the maximization player, a strategy space for the minimization player, and a utility that max and min would like to maximize and minimize respectively. An epsilon approximate maximin strategy for max is some action has action space such that no matter what min does, so for all actions in a min, if we look at the utility obtained when max plays A and min plays B, this is at least the max-min value of the game. So max overall A prime in A's strategy space, in A max's strategy space. Min overall B prime and A min of U of A prime B prime. This is the minimax value of the game. And we're going to allow that it actually be potentially smaller by epsilon. This is where the epsilon approximation is coming in. It might be that there's something clever min can do in response that causes the payoff to be a little bit below the value, the max min value of the game, but not by more than epsilon. Okay, if epsilon were 0, this would correspond exactly to the definition of a maximin strategy. Okay, similarly, B is an epsilon approximate minimax strategy. If B is an action for min, if for every action max has at his disposal, the utility that we get when we play A and B is at most the minimax value of the game, minimum over min's actions, maximum over max's actions of the utility of A prime B prime. This is just the minimax value of the game, and maybe it's allowed to be larger by epsilon. Okay, so this is how we're taking into account approximation, right? The minimax value is supposed to say, a minimax strategy is supposed to obtain the value of the game, or if we haven't yet assumed the regularity conditions necessary for the min-max theorem, either the max-min value or the min-max value of the game, respectively. Here, it doesn't quite guarantee that, but it guarantees something that's not too far off in the direction that you want. Okay, so if you're max, it guarantees the payoff is not too far below that. If you're min, it guarantees the payoff is not too far above that. Okay. So at a high level, the first algorithm we're going to see for computing a minimax equilibrium in a game is going to look a whole lot like the thought experiment that we used to prove the minimax theorem. Okay, with like maybe like a little bit of a twist that's going to make our lives easier in some applications. So if you recall, what did the proof of the minimax theorem look like? We had one player, let's say min, play a no-regret learning algorithm, like online gradient descent. Okay? We had the other player, let's say max, best respond at every round to min's distribution of play, to the sort of vector of play maintained by online gradient descent. Okay, and the way the proof worked is we sort of analyzed the cumulative, the long-run payoff of this game in two ways. First, from Max's perspective, he's actually going second in this interaction, literally getting to best respond. And so the payoff every round is at least the minimax value of the game, because max is really going second and best responding. On the other hand, online gradient descent has a no regret guarantee, right? Which means the cumulative payoff is no worse than the payoff of the best fixed action in hindsight. That's like going back and best responding to the cumulative history of the game. But that would be min going second and best responding. So it was also at most the minimax value of the game, or sorry, the maximin value of the game plus some regret term. That was the first. Okay, so the object we were analyzing was just like a number. What is the long-term payoff of the game? Here we want to prove something about an object, not a number. We want to produce an object that is actually, you know, an approximate maximin equilibrium. Okay, what is that object going to be? Well, the object it's going to be is the the sort of time average of Max's actions over the course of this strategy, right? So in the dynamic for which we use to prove the minimax theorem, every day Max plays some action that is a best response to Min's gradient descent action. There's T rounds of this interaction, so Max plays T actions in the end. What's the thing we're going to return? It's going to be the average of these actions. Remember, under the conditions of the minimax theorem, the action spaces are convex, so we can take the time average that's within the action space. Right, that just corresponds to, in a world in which we've convexified a discrete action space by allowing distributions, that just corresponds to uniformly randomizing between the actions chosen by Max at each round. Okay. So sort of that describe, oh, yes. Yeah. So I'll write this all on the board, which should make it clear. But the first dynamic the first algorithm we're gonna analyze will closely mirror the thought experiment we used to prove the minimax theorem, where there we had the minimization player play online gradient descent because we had derived online gradient descent for cost minimization, and we had the maximization player best respond. Of course, you could swap the roles. Okay, but so I said there's going to be two differences compared to this thought experiment. The first I just mentioned. In the thought experiment, the object of interest was the cumulative payoff. We proved that the cumulative payoff was, up to this regret term, equal to the maximin and the minimax value, and so the two had to be the same. Here, the object of the theorem we need to prove is not the cumulative payoff, but a property of like an actual action for Max that we need to output. We need to actually output a strategy for Max that we claim is an approximate minimax strategy. As it happens, that object is just going to be the average, the time average of the actions he played at each round in the dynamic. Okay, there's another difference, which is that in proving the minimax theorem, we assumed that at every round, Max could best respond to Min's action. Okay, so this was actually stronger than we needed, right? Like, if you best respond to Min's actions, well, you know, you're certainly guaranteed to obtain at least the value of the game. The value of the game is obtained when you best respond to the worst possible action you could have played. But actually, like, to best respond to an action, we require something stronger than that. Not just that you should obtain the value of the game, but that if Min played something suboptimal, if Min made a mistake, that you should be able to exploit that mistake. Right? So like, in rock, paper, scissors, obtaining the value of the game at each round just means that you should never win with higher probability than you lose. But if I commit to just playing rock, if you're best responding, you have to win 100% of the time. Okay? Now in rock, paper, scissors, that's pretty easy, but we're going to encounter some games as we go on in this class for which computing a best response is potentially difficult. Maybe the strategy space is really big and the loss function is complicated. Well, it turns out to make this argument work, and also for the computation of equilibria, we don't actually need you to compute a best response. We don't need you to have the ability to exploit your opponent if they make a mistake. The only thing we need you to be able to do is to guarantee that your payoff at this round is at least the value of the game. Best responding would sometimes require something beyond that, the ability to exploit mistakes by your opponent, but there will be scenarios in which exploiting mistakes by your opponent might be computationally hard, but getting the value of the game is easy. And so one thing we're gonna note in this derivation is that we only require you to be able to obtain the value of the game in response to what your opponent is doing, not necessarily exploit their mistakes. Okay, so more formally, we're going to assume in this algorithm that we have available for one of the players, without loss of generality, max, what I'll call a value oracle, which what it'll do is it's going to take as input an action from min, and it's going to require that you be able to produce an action for max that when played against this action from min obtains at least the value of the game, but doesn't require anything beyond that. So a best response oracle would be an example of a value oracle, but would be stronger than what you need. All right. So let's fix any zero-sum game satisfying the conditions of the minimax theorem. And let's let V be the value of the game. Okay, remember, if the conditions of the minimax theorem are satisfied, we're justified in speaking of the value of the game, which is alternately the minimax or maximin value, which are the same by the minimax theorem. A value oracle for max is some function mapping actions for min to actions for max, such that for every single one of min's actions, when I run the value oracle on that action B, it spits out some action for max, A, such that the payoff against B is at least the value of the game. Okay, and we could equivalently define a value oracle for min, which would take as input an action for max and output an action that's guaranteed payoff at most the value of the game. Okay, so note that if the object we had was a best response oracle, if the object we had was something that, given any action for min, output a best response for max, that would in particular be a value oracle. That would be a stronger object than a value oracle. It would do this and more. I want to sort of make the point that, so we could have that, but I want to make the point here that we don't need that, again, because sometimes this will be an easier object computationally to get our hands on than an actual best response oracle, and this is all we really need. Okay? Yeah. That's right. So yes, so what might a value oracle look like? Well, okay, could be a best response oracle. That would work. It could be a constant function that just always plays a maximin strategy, simpler object than a best response oracle. That wouldn't be particularly interesting for our use case because we want to compute a maximin strategy, but it would satisfy this definition. And maybe gives you some intuition for why there are objects that are value oracles that are not best response oracles. Good. Other questions? Yeah. Yeah, let's see. So a couple of things. So first of all, remember, like we've generally scaled all of our payoffs to sort of be between 0 and 1. But yeah, I mean, I guess more fundamentally, both in the way we proved the minimax theorem and in the algorithms we're going to give now, we're going to take advantage of these no regret learning algorithms we've derived, and regret bounds are inherently additive. So yeah, that's like, yeah, these are not multiplicative bounds. Okay. So how are we going to do this? Let's see our first dynamic, which is our first dynamic for computing a maximin equilibrium. Let's call this value oracle versus no regret. Okay. So this is going to be very much like the dynamic we used to prove the minimax theorem with, again, two modifications. First, we actually need to output some object. Like the claim we're going to make about it is about the property of some object we output, that it should be a minimax equilibrium, rather than just tracking the payoff in the play dynamic. And second, we're not going to use a best response function for max. We're just going to use this weaker value oracle. Okay, so what are we given? Okay, well, a zero-sum game. Satisfying the conditions of the minimax theorem. A value oracle for max, which we'll call val, and a no regret algorithm for min with some regret bound, which I'll write as R of t, saying what min's regret is as a function of t. So if it's something standard like online gradient descent, any of the sort of online convex minimization algorithms we've satisfied, R of t will be some function that depends on scale parameters, but ultimately looks like square root of t. Okay, so what do we do? Well, first, we're going to run some dynamic in which we sort of repeatedly simulate play of the game between max and min for some number t rounds. How many rounds? Well, let's let t be such that the regret bound of min's algorithm divided by t is at most epsilon. Okay, so long as the regret bound is something that grows sublinearly with t, I can take a sufficiently large t such that this is true. In particular, if the regret bound looks like something for the algorithms we've derived, like root t, well, the regret bound divided by t will be 1 over root t. And so the number of rounds we need to take before the average regret is less than epsilon, it's something like 1 over epsilon squared. Okay, so not that many rounds. Now, for each of these rounds from 1 to t, let's get min's action. Let's get action bt from min's no regret algorithm. Let's let AT be max's action, the action that we get when we plug min's action into this value oracle. Okay, so it could be a best response to BT, but more generally, it's just some action AT that when played against BT gets payoff, that is at least the value of the game. And finally, we need to give min's no regret algorithm some feedback. Let's feed a loss function LT, which is just the utility obtained when max plays AT and min plays whatever to min's algorithm. Okay, and then what do we do at the end? We output A bar, which is just the average over each of the capital T rounds of AT, the action played by max, the action output by the valuer. Okay, and just to like, as a sanity check, a game satisfying the conditions of the min-max theorem has convex strategy sets. So A bar is a legitimate thing to output. A bar is in Max's action set because, like it's an average of a bunch of things that Max played, and so it was in his action set, and his action set is convex. Okay, so does the algorithm make sense? So compared to like what we analyzed in proving the minimax theorem last class, two differences. First, we actually output something at the end. It's not just thinking about this sort of dynamic as a thought experiment. It's an algorithm. We output an actual action for max. This is what we output. And second, we don't have max best respond. We just use valuer. Questions? Okay. So what do we know about this algorithm? Well, whenever we can run it, the action output by this algorithm, which maybe I should have given a shorter name, but value oracle versus best response is oh, good point. Value oracle versus no regret. Is an epsilon approximate maximin strategy. Okay. Okay, so the claim is this is a way to efficiently, assuming you have a way to efficiently implement the value oracle, this is a way to efficiently, in something like 1 over epsilon squared iterations, compute an approximate maximin strategy. Also note that we're outputting a maximin strategy for max. We're making no claim, we're not outputting anything for min, and we're making no claims about outputting a minimax strategy for min. We'll think about this a little bit in our next dynamic, and if max was best responding here rather than just using a value oracle, then we could have also averaged together all of min's actions and claimed that those were an approximate minimax strategy for min. But since we're having max here just use a value oracle, that actually wouldn't work. Okay, and maybe just to sort of get some intuition for that, note that, like as Eshwar observed, one way to implement a value oracle, not an especially interesting one if you wanted to compute a maximin equilibrium, but one way, that would satisfy all of the definitions and would be a value oracle would be something, a constant function that ignores min's actions and just plays a maximin strategy, no matter what, right? It just, so in rock, paper, scissors, one legitimate value oracle would just like not be an algorithm at all. It would totally ignore its input, and every, no matter what you plugged into it, it would just output 1/3 rock, 1/3 paper, 1/3 scissors. Okay, so gives, in principle, a value oracle gives, need not give much signal at all to min. Okay, so in particular, suppose the value oracle was just in rock, paper, scissors every day, randomizing between rock and paper and scissors. Well, then, no matter what Min did, she would have no regret, right? If Max is uniformly randomizing between rock and paper and scissors, then everything has no regret. Every action gets the same payoff. It wins half the time, it loses, or sorry, it wins a third of the time, it loses a third of the time, it ties a third of the time. And so the algorithm could do whatever it wanted and have no regret bound. And certainly most things wouldn't be approximate maximin or wouldn't be approximate minimax strategy. Okay, so there is a real asymmetry in this algorithm that comes from the fact that Max is not best responding. Max is just using a value oracle. That asymmetry manifests itself in that it allows us to get our hands on an approximate maximin strategy for Max, but not an approximate minimax strategy for Min. If Max was best responding, this would be an instance of the more general next dynamic we're going to see, which will give us minimax and maximin strategies for both players. Okay? Yeah, Ira. Mm-hmm. Or loss functions. Yeah. That's right. Like we just haven't, like we haven't seen in this class bandit algorithms that can work using only a single number as feedback, right? For all of the no regret algorithms we've studied in this class, just sort of in terms of their type signature, the kind of object they expect back is, in the case of, finitely many actions, a vector that tells you what the cost would have been for each action, and more generally for the online convex optimization setting, a convex function that tells you what the loss would have been for each action. There are algorithms that can get what's called bandit feedback and work to just get sort of the cost actually incurred by the algorithm, but we haven't seen those, and so they're not here. Yeah.
For the algorithm that you have to, you don't need all the loss around.
That's right. So, yeah. So like what the algorithm uses is the gradient of this function at bt. Right. The gradient of the loss function at the so to the extent that you have a way of getting your hands on that information, that's good enough. And in fact, that's how a lot of bandit algorithms are derived. You come up with something that looks like an unbiased estimator for the gradient of the loss function. But we haven't talked about that. But yeah, like the no regret algorithms that we've seen and therefore are using as subroutines expect what's called full information feedback. Good question. Other questions? Okay, so let's prove this theorem. So like clearly, we don't know much about what's going on in this dynamic. The value oracle could be anything. The no regret algorithm could be anything. Like we're gonna need, like all we know is that the algorithm Min is using has some regret bound, and that the payoff every round is at least the value of the game because Max is using a value oracle. So we somehow need to prove this theorem using only those two facts. So let's start with the regret bound. Okay, what does the regret bound say? Well, the regret bound says that if I look at the time average payoff over all t of the rounds actually obtained in this dynamic, so the payoff when max plays AT and min plays BT, and we compare that to the utility that would have been obtained had min consistently played some fixed action B, okay? This is the regret that min has to B, that no matter what B is, so this should be the case for all B in min strategy space, no matter what B is, this quantity is at most epsilon. Okay, the regret is at most epsilon. We've got a no regret algorithm, and we've run it for exactly long enough so that min's regret to any fixed action is at most epsilon. Okay. Okay. Now we need to sort of, right, this is a statement about the time average payoff. Every day, an action, the action that Max is playing is different. It's AT. We need to somehow relate that to the object that we output, which is the, not the average of the, we have to move somehow between the average of the payoffs when Max plays A1, A2, A3, to the payoff that Max gets when he averages his actions, which is a different kind of object. Okay, so I claim, first of all, that this is at least, well, okay, the first term is unmodified. Let's just separate that out. Okay, so the first term is the actual time average payoff in the game, the utility obtained on average over all of the rounds when Max plays AT and min plays BT. Okay. Minus the utility obtained when Max plays A bar, plays the action that is the average of the actions he's played so far, and min plays B. Okay. Yes. I'm a little confused, but you mean BT is in A min? A min is just the, what did he say? Yeah, BT is an action for min, and A min is min's action space. Uh-huh. Okay. Yeah, so that would be fine. And also, like, if you're min, you're playing a no regret algorithm, so you can't do like arbitrary stuff. And this is just what the no regret algorithm guarantees, that your payoff as min is at most the payoff you would have gotten had you played some fixed action B plus epsilon. Okay, cool. Okay, so I jumped in this line from talking about like the time average payoff against B when Max plays A1, A2, A3, to talking about sort of the one-shot payoff against B when Max plays the average of these actions. Why was that a justified step? Well, remember, since this is a game that satisfies the conditions of the minimax theorem, one of the conditions of the minimax theorem is that this utility function for every fixed B, for every fixed action of min, must be concave in Max's action, right? Like the maximization player should be maximizing a concave function because that's what you want to do. And so what does that mean? It means that once we fix B, this trick wouldn't work over here when B is different every time. But over here it works because B is fixed, where we've just got a single B. Once you fix B, if we look at Max's payoff as a function of A, the action he plays, it is a concave function. The way I learned in elementary school to remember the difference between convex and concave, which are otherwise like symmetric, is that concave functions look like a cave. if you remember one thing in this class, concave functions look like a cave. What did you say? Community day school in Pittsburgh. Okay. Okay, concave functions, they look like a cave. So what are we doing when we're looking at the time average payoff of Max's various actions? Well, the payoff of Max's actions are like evaluations on this curve. And when we average the payoffs, that's like drawing, a line interpolating between the 2 points of the payoffs. Now, the fact that this function is concave and therefore looks like a cave means that this line lies below the function. And so if we move from evaluating the average of the function values to the function of the average values, we move up to the point on the curve. We get a thing that's only higher. Okay, this is called Jensen's inequality. And so that means that the evaluation of the function on the average of the points, this is only a bigger number than this, the average of the evaluations on the points. And if we're subtracting off a bigger number, then we get something smaller. Okay, so here we're using the fact that a utility function in a zero-sum game satisfying the conditions of the min-max theorem is a concave function of Max's actions, fixing Min's action. Okay, so that's what allows us to say something about the utility for the average action, which is the object output by the algorithm. Make sense? Everyone with me so far? Okay. So we're almost done. This is the quantity we want to have a statement about in the end. We want to say that A bar is an approximate minimax equilibrium, an approximate maximin equilibrium for Max, which means that this payoff should be within epsilon of the value of the game, no matter what min does, for all B. Okay, so let's start by rearranging this expression so that at least the object we want to prove something about is on the left-hand side. So rearranging, what do we get? Well, we get for all of Min's actions, the utility that we get when Max plays A bar, this thing that is hopefully an approximate maximin strategy, and Min plays B, it's at least the sum over all of the time steps of the average over all of the time steps of the utility obtained when Max plays AT and Min plays BT minus epsilon. Okay, all we've done is we've moved this expression to the right and we've moved the epsilon to the left. Okay. But what do we know about this expression? Well, Max is choosing his action every day with a value oracle. So we know term by term, every term in this average is at least V. That's the definition of a value oracle. No matter what, it gets payoff at least V. Doesn't have to be a best response, but does have to get payoff equal to the value. So this is at least V minus epsilon. Here we're just using the definition of a value oracle. And this is the definition of what it means to be an epsilon approximate maximin strategy. It says that, look, if you played optimally, if you played a true maximin strategy, then no matter what your opponent did, you'd be guaranteed payoff at least the value of the game. An epsilon approximate maximin strategy says no matter what your opponent does, you get within epsilon of the value of the game, which this is. Okay, so a no regret algorithm paired with a value oracle gives you an algorithm for computing an approximate maximin strategy for the player you have the value oracle for, not for the other player. Okay, makes sense. So like whenever you can do both of these two things efficiently, implement a no regret algorithm for one player and implement a value oracle for the other player, right? In large action space games, it may be non-trivial to do either of these things, but when you can do both of these things, then you have an efficient algorithm for computing a minimax or maximin strategy for whichever player you were able to implement the value oracle for. Make sense? Okay. Maybe one thing that's sort of worth remembering as we sort of try to use this going forward as like a concrete like computational object. There's already some approximation here, right? Like basically because no regret algorithms have regret tending to zero, but not necessarily ever being zero. This kind of algorithm doesn't give us an exact maximin equilibrium strategy, but just an epsilon approximate one. Okay, so for the same reason, like we assumed that we had access to an exact value oracle, but if we were okay with epsilon approximations anyway, like if we wanted to recover this theorem, but with a 2 epsilon instead of an epsilon, it would have been sufficient to assume we have access to an epsilon approximate value oracle. And the only difference in the analysis would have been here, the payoff every day would have been at least v minus epsilon, and we just would have gotten 2 epsilon here.
So that this allows us if you're setting words to have a value oracle and also no regret. Are those like how do you compare the how hard of an ask are those?
Let's see. We will see actual settings where both players have exponentially large strategy spaces. So none of this is straightforward, for which I know how to implement a no regret algorithm for one of the players, say because their payoff is linear, and so you can use follow the perturbed leader. And I know how to implement a value oracle for the other player, but not a best response oracle. But not the other way around, meaning I guess I could implement a value oracle for the linear player, but I don't know how to implement, like there's a player for which I neither know how to implement a no regret algorithm or a best response oracle. So, well, it's for 2 different players in the same setting. It's a good question. So is there ever a case when that's right. Yeah, you're right. You're right. So I guess like if you have the ability to implement, like having the ability to implement a no regret algorithm, for the reason Eshwar said, is like a strictly stronger thing than implementing a best response oracle, which is itself a stronger thing than implementing a value oracle. Because yeah, if I run a no regret algorithm on a fixed instance, the same payoff every day, the only way it can get no regret is by converging to a best response. That's right. So it's a stronger ask to have a no regret algorithm. And then often, right, often what you're looking for when you have a large game, if you have a game with finite strategies for both players, you could just implement whatever you want for either player. When the games have sort of large strategy spaces, it's important that you be able to implement a no regret algorithm for at least one of the players. That is the strictly stronger of the 2 objects. And for the other player, right, so there should be like an easy player, maybe their payoffs are linear or something, so you can implement follow the perturbed leader. The utility function can be, the utility function is a function of both of their actions. So it could be linear in one of them, but not the other. Yeah, so a no regret algorithm is a stronger object than a value oracle. And so, okay, in the dynamic we're going to see next, we're going to assume we have the ability to guarantee no regret for both players. That is a stronger ask than what this is doing here. There are cases when you can't implement no regret for both players, or even implement a best response oracle for the more difficult of the two players, but a value oracle is okay. The cost we pay for that is that, interestingly, the player that has, for which we have the weaker abilities, we can only implement a value oracle, not a no regret algorithm. That is the player we get the approximate maximin strategy for, not for the other player. Okay, there's real asymmetry here. Okay. Okay, so let's now think about another way of computing approximate maximin and minimax strategies. Just to like note, here we've sort of arbitrarily assigned max to play the value oracle and min to play the no regret algorithm. Everything's symmetric. We could have swapped their roles, in which case we would have computed an approximate minimax strategy for min. Okay, you always get the minimax strategy for the player who's using the value oracle. But now let's sort of think about sort of a scenario where the game is better behaved, and so we have the ability to implement no regret play for both players. Okay, that would be a different dynamic. Because a value oracle does not output a best response, by the way, like the value oracle player does not a priori have like no regret. Right, like again, like if you are playing as max, a minimax optimal strategy, you're randomizing between rock and paper and scissors, you're getting the value of the game. But if I'm playing rock every day, you have regret to paper. Okay, so like here, it's not the case that both players have no regret. The value oracle player might have a lot of regret. But suppose we actually have the ability to implement a no regret algorithm for both of the players. That's a strictly stronger ask. Then we will get a different algorithm that will compute a minimax and a maximin strategy, respectively, simultaneously for both players. Okay, so what's the theorem? Fix a zero-sum game satisfying the conditions of the minimax theorem. Let's suppose we have a sequence of pairs of actions for both players, AT, BT, where time ranges from 1 to some capital T. Suppose this sequence of actions has epsilon average regret for both players. What does that mean? That means that if I look at the time average play of this sequence of actions, I simultaneously know that this is at least the time average play of the best action for max against the realized action for min minus epsilon. This is a regret guarantee for max that given the realized sequence of play, the time average utility is at least the time average utility of the best action max could have gotten in hindsight minus epsilon. This is a regret guarantee for max. So as I simultaneously know this, and I know a regret guarantee for min, that simultaneously the same time average play is at most the time average play of the best action available to min plus epsilon. So this is a regret guarantee for min. It says that the time average play for min, the same time average play as before, is also at most the cost she would have obtained with her best fixed action in hindsight against the same sequence of actions played by max, possibly worse by epsilon. So we're asking for simultaneously a regret guarantee for max and for min. Whenever we have a sequence of such actions, then if we say that A bar is the average of the ATs, and B bar is the average of the BTs, then A bar is a 2 epsilon approximate maximin strategy. And symmetrically, B bar is a 2 epsilon approximate minimax strategy. Okay. So a couple of things to note. So first, like the way I stated this, it's just a statement about sequences of actions that happen to satisfy this no regret guarantee for both players. I didn't say anything about where it came from. But algorithmically, there's a few ways you could get your hands on a sequence of actions that has this property. For example, you could just run a game dynamic for T rounds like this, in which both of the players are playing using no regret learning algorithms. They could both play according to multiplicative weights or gradient descent or follow the perturbed leader, or you could mix and match. Okay, that would be one way to do it. You could also play with one player playing a no regret algorithm and the other player best responding. If I'm best responding rather than playing just a value oracle, I will have 0 regrets, right? I will do as well as the best fixed action in hindsight overall, because day by day, I'm doing as well as the best action on that day. I'm best responding. So if we modified this to be no regret versus best response rather than no regret versus value oracle, that would be one way to produce such a sequence. Okay, there's various ways to produce a sequence like this. Whatever way you choose, you've got this guarantee that you converge to 2 epsilon approximate minimax and maximin strategies. In fact, it doesn't care about the details of the algorithm. People could actually be playing in the game using whatever heuristics they have to play in games. They don't need to be guaranteed to have no regret in the worst case. If what they do happens to have no regret or epsilon regret, then this says their empirical sequence of play must converge to an approximate Nash equilibrium of the game. Remember, we showed that minimax and maximin strategies form Nash equilibria of zero-sum games. Okay? And then note also that this is not the same statement that we made here, because in this sequence, min does not necessarily have no regrets. Or sorry, max does not necessarily have no regret. We gave an example in which max could be playing a value oracle at every round and not have no regret. So the theorem we proved about value oracle versus no regret is not a special case of this. Okay? Here we've assumed something a little bit stronger, but we've also gotten a stronger conclusion that we've computed an approximate minimax and maximin strategy respectively for both players. Yeah. That's true. Yeah, I mean, this is not a theorem about a worst case regret guarantee, but about the realized one. I think that may also have been true about our analysis here. So like, I think in our algorithm, we used the existence of this worst case bound, but you could have replaced this stopping condition with the condition that empirically there's no regret to any action. I think that analysis would have still gone through. So that's not a difference, but it is a strength of both cases that if your algorithm happens on this sequence to get better regret bounds than its worst case bound, you can stop early. And in fact, like if you have the ability to compute best responses, you can just evaluate what is your current regret bound, and you can stop at that point. Yeah.
Of the asymmetry here is that is like maybe lies more in the action space of the other person and like their chaos instead of yours.
Yeah, it's somehow like if you want to compute a maximin strategy, it's important that your opponent be playing well. Like your opponent playing well gives you the feedback you need to compute a maximin strategy. You don't necessarily need to be playing that well. If you are only playing a value oracle, if the other person's doing something really stupid, you're not necessarily learning much about the game, right? Another interesting thing here, right? Like in none of these algorithms, like do we tell either player like what the game is, right? Like in principle, the game is given to us, like we know, like for every pair of actions, what the payoff is going to be. But neither player's algorithm has access to that information. They just play the game. The feedback they get, the feedback the no regret algorithm gets is just, like the losses given what your opponent happened to do this round. That's what drives the analysis. So like in some sense, like if your opponent is not playing well, if you Max are playing some value oracle, but your opponent is not playing well, you're not getting the feedback you need about what the game is to converge to like this object, which obviously needs to be defined in terms of the properties of the game. Well, so so let's think about the minimization player who's playing this no regret algorithm. They're the ones whose opponent is not necessarily playing well. Like their opponent is not exploiting their mistakes. Their opponent does not have a no regret guarantee. And so it's for the no regret player, the minimization player, that we're not necessarily getting an equilibrium strategy. So what kind of feedback do we give to like online gradient descent, the minimization player? It's not the whole payoff matrix. It's like the part of the payoff matrix that corresponds to the action your opponent actually played. So if they always play the same thing, they're playing in some dumb way or some non-responsive way, like they just play a maximin strategy, then you're just not getting feedback about large portions of the payoff matrix. And so you don't have the information to converge, right? And so the person playing the value oracle, they're getting all sorts of feedback because the no regret player needs to, do interesting things in order to promise this no regret guarantee. But the person playing the no regret algorithm, they're playing against someone who's potentially a dummy and is not exploiting their mistakes. And so they're not getting enough information about the game. Does that make sense?
Some lower bound like if this was like random play, or this was like about someone going with no regret, where that's what does right? Like, if I just was left or whatever. So also like in order for me to be like I need to force no regret also to like be interested by playing.
Yeah, so somehow like a no regret player is sort of smart enough to force a value player to converge to a equilibrium strategy. A value player is not smart enough to force a no regret player to converge to an equilibrium strategy. Like somehow your opponent needs to be pointing out your mistakes when you make them. So the value player is pointing out the mistakes of the no regret player. right, places where they have left themselves open to potentially having payoff, like worse than the value of the game. But these are all good thoughts. I'm mostly responding off the cuff here and without having like thought these things through carefully. I think this is an interesting collection of questions. Like, why is it that we get an equilibrium for the value player and not for the no regret player? It's sort of the opposite of what you'd expect. The player for which we've implemented a less sophisticated thing, we're computing sort of the stronger object. So I'm not claiming I know the complete answer to that question. Maybe it's worth pondering. Okay. But suppose we have no regret for both players, which we could do either by running two no regret algorithms against one another, or no regret versus best response, but importantly, not no regret against a value player. Then the claim is that when we just average the sequence of plays simultaneously for both players, both of those, the average play for max and the average play for min, are approximate equilibrium strategies. Mm-hmm. So I guess, right, a best response oracle would allow you to verify that you have a maximin strategy. And therefore, a no regret oracle would allow you to do it, but a value oracle doesn't. Yeah, so maybe like the object that min is playing against here isn't enough even to confirm that they've found a maximin strategy. And that should give us some intuition, at least. That's probably not enough to find it either, because usually confirming the task is like a necessary prerequisite to like solving it. That's a good point. Okay. So let's prove this theorem, which really, corresponds to a couple of concrete algorithms. As we've said, no regret versus no regret versus best response. Those all would produce objects that satisfy the conditions of this theorem. It's a symmetric theorem, so I'm going to prove the statement about A bar, that A bar is a 2 epsilon approximate maximin equilibrium, but there's complete symmetry here. Like, we've assumed nothing different between, max and min here. So exactly the same argument would prove the claim about B bar. Okay. So remember, we start with sort of a two-sided regret guarantee, a regret guarantee for max and a regret guarantee for min. We're going to need to use both of these at some point, but let's start by using max's no regret guarantee. Okay, and we're going to use Jensen's inequality again as well. So for max's no regret guarantee, what do we learn? Well, that's just the right-hand side here. Okay, so just transcribing that. We learn that the time average payoff over this whole interaction is at least the payoff that Max would have obtained by playing the best fixed action in hindsight against the sequence of realized plays by min minus epsilon. This is just literally reading off Max's no regret guarantee. And applying Jensen's inequality, this is at least the maximum over all of Max's actions of the payoff they would have obtained playing action A against B bar minus epsilon, where B bar is the time average of min's plays. Okay, and let's just like confirm this, because normally Jensen's inequality goes in the direction opposite what you would like. So let's just like make sure it goes the right direction this time. Right, so remember, games satisfying the minimax theorem are concave in Max's actions and convex in Min's actions. Remember, concave functions look like caves. So what that means by process of elimination that convex functions must look like this. Okay, so up here we have the time average payoff. So that's like taking multiple points on the function, the utility function, and averaging them together, which interpolates them along this line. But for convex functions, the line lives above the curve. So if we move to the evaluation of the function on the average of the payoffs, we've made the utility function only smaller. And so we're justified in using the inequality in this direction. Okay. Yeah, if you learn nothing else in this course, figuring out when Jensen's inequality goes in the right direction is a good trick. Yes? Nope. A is a fixed argument here, right? So, yeah, I mean, I'm not using anything fancy, but like I guess, yeah, like, that this is greater than the maximum of all of these things. That's the same thing as saying it's greater than each of them, right? So I could say for all A, this is true. And then the max doesn't have to scare you because it's not here. Yeah. But yeah, I guess I am using that fact. Okay, good. Okay, Jensen's inequality. Okay, well, this is, like this is Max's best response to like something that Min did. So this payoff is only higher than Max's best response to the worst possible thing Min could have done for Max's payoff. So the min, the action that minimizes Max's payoff after he best responds. Okay, right, like if Max is best responding to something, he's only getting payoff that's higher than if Max is best responding to the worst possible thing Min could have chosen for that purpose. But this is the min-max value of the game, which, because the minimax theorem holds, it's just the value of the game. So this is at least the value of the game minus epsilon. Okay, so we're not done yet, but we shouldn't expect to have been done because we've only used the no regret guarantee in one direction so far. What have we done, by the way? We've related the, like B hat here only played a sort of supporting role in the middle of this argument. There's no B hat at the beginning or the end, right? So this isn't a statement about A hat or B hat. This is a statement just about the time average payoff. The time average payoff is at least the value of the game minus epsilon. That follows from the regret guarantees. Okay, so we need to use the other regret guarantee as well. And Jensen's inequality in the other direction. So let's start with Jensen's inequality. So we have that for each of B's actions, or for each of Min's actions B, if I look at the utility that A would get if he played A bar, this thing that we're hoping is a approximate maximin strategy against B, we have that this is at least the time average overall T rounds of the payoff if Max were to play AT at each round against this fixed action B. This is just, again, Jensen's inequality, the utility function is concave in Max's actions, and so time averaged payoffs are only time average payoffs, the thing on the left, the thing on the right, are only smaller than payoffs of the average strategy. Okay, so this is just Jensen's inequality applied to a concave function. But this thing, by the regret guarantee, the other regret guarantee, the one we haven't used yet, is at most the time average payoff of the game when Max plays AT and Min plays BT minus epsilon. How come? This is just the regret bound. The regret bound, this side of the regret bound tells us that the time average payoff is at most, is the regret bound for Min. The time average payoff is at most the payoff for any one of Min's fixed actions in hindsight plus epsilon. Okay, first line Jensen's inequality, second line Min's regret bound. Okay. But this is at least V minus 2 epsilon. Because we just proved over here that the time average payoff, this thing, was at least V minus epsilon, and we already had an epsilon hanging around. Okay? And this is the statement we wanted. This says, if Max plays A bar, then he's guaranteed payoff, at least the value of the game, possibly less by 2 epsilon, no matter what Min does, or equivalently, A bar is an approximate, 2 epsilon approximate maxi-min strategy in the game. Okay, so we have two algorithms now. So we've used these no regret algorithms now to both existentially prove the minimax theorem, last class, and this class actually give us two different concrete dynamics that allow us to, to like computationally get our hands on maxi-min and minimax strategies. Whenever we're in a position to implement no regret algorithms for the two players, then we can symmetrically get minimax and maxi-min strategies for both of the players. If we can't do that, we can implement a no regret algorithm for one of the players and a value oracle for the other, which is a weaker object. We can still get a minimax strategy for the player for whom we can evaluate the value oracle. Okay, so thank you. Next class, we'll start trying to put this machinery to work.